Now let's study image formation by a lens. As we did for mirrors, we will locate the image by tracing certain principal rays that are easy to find as they move from a single point on the object. Remember, however, that though we consider only a few principal rays here, light rays from this point strike all parts of the lens, and all of them contribute to the image. The first ray goes in parallel and out oriented with the focus. With a converging lens, the light ray travels through the focus on the far side of the lens. With a diverging lens, the parallel ray is bent by the lens and leaves the far side as if it came from the focus on the near side. The second ray, as it approaches the lens, is aligned with one of the focal points, but it leaves the lens traveling parallel to the lens axis. With a converging lens, the light ray actually passes through the focus on the near side of the lens. With a diverging lens, on the near side of the lens the light ray is directed towards the focus on the far side, and then at the lens it turns parallel to the axis. In general, these two rays suffice to locate the image. However, if the two focal points are equidistant from the lens, a third locating ray can be drawn. This ray extends from the object and passes through the center of the lens where it meets the lens axis. Because the ray goes through the center of the lens where the two lens surfaces are parallel, it does not bend. The image produced by the converging lens is now obvious. In this case, it is a real inverted image that is bigger than the object. For the diverging lens, the image is slightly more difficult to find. Because it is a virtual image, we must trace the outgoing rays backward until they cross. This reveals a virtual upright image that is smaller than the object. Keep in mind that we considered only two simple examples of image production by lenses. In this case, the image from the converging lens was real, but sometimes images from converging lenses are virtual. Finding them will necessitate tracing outgoing rays backward. Except for the equation relating frequency to mirror radius, the equations we use for mirrors also apply to lenses. As with mirrors, the focal length is positive for a converging lens and negative for a diverging lens. The image distance is positive if real and negative if virtual. The object distance is almost always positive. Lens magnification is positive if upright and negative if inverted. The lens equation is used exactly as the mirror equation is, and the chart explaining where to expect the image and the image's characteristics is also the same. We now know how to find and describe the images created by a single lens. But what happens when two or more lenses are involved? In such cases, the image of the first optical element serves as the object for the second lens. Notice that process produces an upright real image. A wide variety of optical instruments, such as telescopes and microscopes, take advantage of image produced by combinations of lenses and mirrors.